Hello everyone, my name is Xiaoma from Shanghai Jiaotong University and Lenovo Research. Thank you for being here. Today I'm presenting our ICMR 2026 paper, SlimNet, High Quality and Efficient Object Removal by Eliciting Latent Capabilities of Diffusion Models. As you can see in these examples, our method removes the masked object cleanly, keeping the color and texture of the field region consistent with the surrounding background, and without leaving visible boundaries or artifacts. I'll walk you through how we achieve this efficiently. Let me start with the problem. Object removal aims to eliminate undesired objects from an image while plausibly restoring the undesired content with high visual fidelity. It's a functional editing capability, and it matters most on device, where users want real-time photo editing and tight computational budgets. With the rise of generative models, diffusion-based methods have pushed the visual quality well beyond early CNN and GAN-based painting, thanks to their iterative denoising process. But they pay a steep price. Strong results usually depend on large-scale fine-tuning, auxiliary control networks, or very large diffusion backbones, heavy computation that limit real-world deployment. This leads to our key observation. On the right, object removal is not the same as text-to-image generation. The goal is faithfully background computation, not synthesizing diverse new objects. Pre-trained diffusion models already hold this ability. The real challenge is to elicit and constrain it rather than scale the model up. Concurrently, existing diffusion-based methods face three barriers. First, artifact generation. Strong generative prayers can hallucinate unintended objects or artifacts in the removed region when the constraints are too weak. Second, heavy computational cost. Achieve high quality typically requires large-scale fine-tuning, auxiliary control networks, or large backbones, expensive in both training and inference. Third, manual annotation cost. Co-created pair datasets and hand-drawn masks are costly to build, which limits scalability. Our response, summarized at the bottom, a parameter-efficient firm access elicits the latent removal ability already inside the model instead of scaling the backbone. So here is SlimNet, a lightweight plug-and-play adapter framework built on Frozen SD3 diffusion backbone. It resists on three contributions. One, lightweight adapter architecture. We inject linear slim adapters that modulate intermediate features. Only the adapters are trained, about 94% fewer trainable parameters than control-net-based methods. Two, a composite perceptual loss that jointly enforces foreground removal accuracy, background preservation, and smooth foreground-background transitions, suppressing artifacts and sieves. Three, a semantic-aware data pipeline that automatically generates object-aligned training masks, removing the need for manual annotation and improving training stability. I will go through each in turn. This is overall framework. The original image and mask are encoded into the latent space, and the text promo is fixed to a neutral face, background, nothing, blank. The diffusion backbone, here SD3, built from MMDIT blocks, stays completely frozen, shown by the snowflakes. Alongside, if we attach SlimNet, one slim adapter per block. As shown on the right, each adapter applies a simple per-layer transformation. It takes the layer's feature map together with the binary mask M and the noisy latent XT and passes them through a lightweight linear layer. The transformed feature is added relatively back to that block's output as a parallel branch in the figure shows and flows into the next block. Because only these linear functions are updated, we add just 0.1 to 5 billion trainable parameters while keeping the full generative power through the backbone. This is the core of SlimNet's efficiency. We don't rebuild the model, we gently steer it. To surpass artifacts and ensure fidelity, we train a composite loss. The equation at the top combining four terms. Flow matching loss is original diffusion objective over the whole image. It preserves overall generation quality. Foreground perception loss is computed inside the mask. guiding sharp, detailed reconstruction of the field region. Background perceptual loss is computed outside the mask, ensuring the backbone stays unchanged during removal. And the bounding box perceptual loss, one of our key designs, we take the minimum enclosing rectangle around the masked region and match the generated content to its surrounding background context. This excited harmonize the field region with its neighborhood, removing the halos and color discontinuities that otherwise appear white at mask edges. Together, these terms cover what to remove, what to keep, and how to blend the scene. Training is data, and we generated it automatically with no manual annotation. The pipeline has 4 steps. We start from raw line images, about 600,000 of them. We run YOLO to detect foreground objects. We then place random masks, polygons, and rectangles only in background areas, and we discard any mask that overlaps a detected object. Why constrain mask to the background? Because in object removal, the content to synthesize after deleting an object is almost always background, like sky, wall, road, texture. If we instead mask complex foreground during training, we amplify hallucination and boundary artifacts. By focusing the training signal on background completion, the core skill for removal will lower the difficulty and improve stability. This is the data side counterpart to our architecture efficiency. Now the experiments. We evaluate on 2 datasets, real enriched HQ, our 1,568 high-quality real-world images with objects removed by professional annotators, and the RD test set with 934 pairs. We report PSNR, SSIM, FID, LPIPS, and the reference-free remove score against Llama, SD3 painting, Clip V, and OmniPaint. The highlighted row is ours. Bold marks the best per metric. On Real Erase HQ, SlimNet achieves the best LPIPS and ranks second on the rest. On our RD, we obtain the best PSNR and best remove, and second on SSIM and LPIPS. So across every metric, SlimNet ranks first or second, strong perceptual quality and removal completeness. And as we'll see next, at a fraction of the cost. The numbers are matched by the visuals from left to right, original mask GT hours, then the 4 baselines. Llama tends to produce blurry field regions, as this ring painting generates detail but can hallucinate objects or artifacts. Clip-free often fails to fully remove the target. And OmniPaint, while powerful, loses fine texture and notably can be over-aggressive, removing shadows outside the user's mask, as in the fifth row. In contrast, SlimNet strictly respects the mask boundary, producing sharp detail and seamless background integration closest to the ground truth. Here's where efficiency becomes concrete: total parameters, inference time, and VRAM. Compared to SD3 in paintings, SlimNet cuts trainable parameters by about 94%, 0.125 billion versus 2.08 billion on the same lightweight backbone. That translates directly into system performance. Inference in just 30 seconds, more than 3 times faster, and VRAM down to 22 gigabytes. OmniPaint looks tiny in trainable parameters while lower, but that hides its backbone. It rides on Flux, a 12 billion parameter model, roughly 6 times larger than SlimNet in total, needing 19 seconds and 34 gigabytes. The takeaway, high quality removal does not require brute force scaling by eliciting the latent ability of a compact model. SlimNet matches all base large model approaches at a fraction of the cost. Finally, ablations confirm that each loss term earns its place. The table shows the local perceptual loss on Real Erase HQ. The full model wins on every reference-based metric, PSNR, SSIM, FID, and LPIPS, and dropping any single term degrades fidelity. The figures on the right make this visual. Without the foreground loss, the field region goes blurry. Without the background loss, we see drift and color shifts outside the mask. And without bounding box loss, halos and discontinuous appear as edges. Each term targets a distinct feeder mode: foreground detail, background preservation, and seamless boundaries, and together they deliver clean, coherent removal. To summarize, SlimNet elicits the latent object removal capabilities of a frozen pre-trained diffusion model, reaching state-of-the-art quality with only a fraction of the parameters and compute. Our four takeaways: a lightweight adapter design with 0.125 billion trainable parameters, a composite loss for accuracy, fidelity, and seamless edges, an automatic semantic aware data pipeline, and efficient deployable inference, 30 seconds and 22 gigabytes. For future work, the adapter design is model agnostic. We can plan more efficient adapters and extensions to stronger backbones and other editing tasks. Thank you very much for your attention.